All right, Electrical Apprenticeship, Year 3. We're looking at line P3, and we're still working on learning task 2, which is this really long one about how we make our transformer connections. We're into the very last section of it now, which is where we're going to deal with some specialty, weird type of connections. And they're not something you should expect to go and run into in the field very often. If you do, you have to know what to be able to do with them. If you get tested on them, you have to know what to be able to go and do with them. But it is not going to be your most common types of connections you're going to run into. And these are going to be your open delta, as well as your 4-wire delta, as well as your open Y, open delta. A couple of things we want to talk about, starting on your page 51, where they start talking about special 4-wire delta connections, is that if we've got a delta connected secondary of a transformer, there's no ground on the system. And if you have no ground on the system, you don't have a neutral on the system, and you have no way to go and deal with your single-phase loads, lights and receptacles and things like that, that people generally inside of places of business are going to go and need. What you're able to do is you are able to go and create a special type of system. One of these over here, which is going to be a 4-wire delta system that is going to be fed as a delta system, but it's also going to go and have one of its transformer windings, this winding right over here, that is going to be center tapped. And you're usually, and although they're rare, you're usually going to only see these on a 240 volt delta type of system. Because if it's a 240 volt delta system, that would mean that if this one is center tapped, we would be seeing values of 120 volts and 120 volts that we would go and have on either side of that for our single-phase system. What we'll do is we will go and take these systems, and then we're going to go and feed these lines. And we're going to go and feed, over here we've got our A line. And what we're going to do is we're going to go and create 2 separate panels with these things. So coming off this transformer's connection, you're going to go and have your B line, and you're going to go and have your C line. And these are going to go into a 3-phase panel that has no neutral. Has to go into a 3-phase, no neutral. Okay, those 2 are going to get fed into there, and then out of that one, we're going to distribute out to our different loads that we're going to go and have on the place. You're going to have your motor loads, you're going to have 3-phase heaters, anything like that, that are going to get distributed out of there. We don't want a neutral in that panel because we don't want people fooling around trying to make single-phase connections inside of it. What you're also then going to be able to go and do is take your other lines, your B and your C line, and your B line, and your C line, and your neutral that you have created by center tapping this transformer and grounding it down, are all going to go and get taken, and they're going to get put into another panel over here. So you're going to come off that transformer, you're going to feed lines to these ones over here. And inside of that panel, you are then going to go and have the option to do single phase. It will have to be a single phase panel. 1-phase panel. It's obviously going to go and have a neutral bus that this is going to go on. This would become your line 1 and your line 2. Although they aren't line 1, line 2, it's not phase A, B, and C. It's a single phase line 1, line 2. And so you would be able to distribute all of your single phase loads out of that panel itself. You're never allowed to combine all of these together into the exact same panel. Having a 3-phase panel with a neutral inside of it is allowable. It's doable on a 122.08 volt system, but not on one of these systems, because what could accidentally happen if I were to go and take, and I'll just erase this good setup that we have over here and show you a dumb setup. If I were to go and take this neutral from here back in and place it in like that, there is a danger that somebody might go and run out a line from my phase A and a neutral, or what they think is a neutral, from my phase, or from my neutral there, put a load across it thinking that they're going to get 120 volts. They're not. What they're actually going to go and measure across here is going to go and be 208 volts. And if you place 208 volts over top of a 120 volt load, you are going to go and have fire, explosions, things like that. Bad times are going to ensue, so we just want to stay away from that type of a thing. The code book tells us that we have to go and make sure that this can't happen. We have to go and, first of all, anytime that one of these systems would be used, we have to always make my A phase what they refer to as the high leg, or the leg that is furthest away from the neutral. So we'll call this one the high leg over here. And we have to go and make sure that this A high leg does not enter the same panel boards as what I'm going to go and have for my single phase connection that I'm going to take off of here. Uncommon to go and have one of these transformer connections because they're a difficult transformer to go and obtain. It is far more common that if you have a delta type of system, you're just going to use the delta transformer to supply your three-phase loads, and then you'll just grab a single phase transformer. You'd be able to get a 240 center tap transformer. Actually, it would just be an auto transformer that you would just tap across that, and then you would be able to create a neutral from that one. If you do go with this 4-wire delta connection over here, you do have to go and watch the amount of power that is going to be put out by your different ones, because your windings are going to become unequal. And I've taken a snip of what that says inside of your book over there. It says that this winding over here is going to go and supply 2/3 the current to the single phase load, and the other 1/3 is going to be taken by the other two windings. Not at the same time, so they're not each getting a 1/6, but this one's going to be delivering that last third, and then this one. And then the other one, and then the other one. They're just going to alternate back and forth who's delivering that last third out to. It makes sizing for these a little bit more difficult, and we will go through a little bit of sizing off of them later on. Be very careful with these. Once again, very rare that you're going to go and run into one of these. Just in usually industrial places that are almost all three-phase motors with only a tiny little bit of lighting and power usage might be the only place you will see them. Outside of that, hardly ever going to run into them. The next one that you're going to go and see is what we refer to as our open delta transformer bank. And an open delta transformer bank is where we just use two transformers on a three-phase system. So I have an existing three-phase system, and I only use two transformers to go and step that down. And there's a couple of reasons that we might do this. We might do this just because it's a stopgap measure. You know, we might have had a bad failure on one of our transformers. Maybe there used to be a third transformer inside of here, but that third transformer is bad right now. Something happened to it, and so we've taken it out for repair so we can just operate at a smaller kVA. Other times, we might place only two smaller transformers in, knowing that in the future, there's a good chance that my customer is going to go and be expanding, and later on, we might go and add in that third transformer when they, have the budget for it, etc. This also isn't the most common, and if you're dealing with somebody that's too cheap to put a proper system in at the very beginning, there's a good chance that it's a job that's going to go sideways anyways. I would walk away from that, because if they can't put the money in up front, there's a very good chance they're going to go and nickel dime you the rest of the way through. The last one that we might have is where I'm going to go and have the majority of my load that's going to be single phase, and I only need to have a very small amount of three-phase power. And for those type of situations, it might be where you have got a 240 volt delta line that you are feeding in. So you might be 600 on the top there, but you might be coming over to 240 volt, and you're having all loads and loads of line to line. We're just going to go from A to B. Lots of heat or something like that. That's going to be single phase 240 volt components, but then you do have a couple of small rotational motors. You might throw one of these in. Generally speaking, that's going to be something more that'll be inside of a machine rather than anything else. These ones, I'm just going to erase all of this over here. These ones over here are going to have a phase of representation that's going to be a little bit different than what we're used to. We do follow a bunch of conventions. We start by drawing in my A. We start by putting in that line to neutral, and then we go and place in my B as we normally would. And then A to B is going to go across there. We stick our H1 over here. We're going to go and have our B, H1 up top here. We're going to go and have our C, H1. Would be normally down here, but we're not going to have a C winding in here. So this would normally be where we have a C1, but we're just leaving that thing out. Because on my side that I'm supplying, whether it's going to be as a step up or as a step down, because I already have a three-phase line that's supplied to it, that means that I'm going to go and have two out of the three lines that I'm going to go pass down to the secondary side. So in reality, we see that we've got these arrows over here and arrows going here. We see that my secondary or my low voltage side is going to go and have the same arrows. And because the phase displacement on the primary side already exists, it is going to go and hold those lines apart. It's basically going to create anchor points to our system that are going to allow this to exist on the last phase or on what we would refer to as our ghost phase at that point. It does mean, though, that I am going to go and have some weird kVA values for these things. Because when I take a look at it, normally inside of an actual true delta system, I'm going to go and have two currents that are going to combine to go and form one supercurrent. We call that supercurrent the line current, and we call these two smaller currents the phase current. But I don't have that option when I'm looking at open delta. On one leg, this one over here, I could get combination. But on this one over here, I'm only ever going to be able to get a single line out. Same with this one over here, I could only ever get a single line out as well. So we're going to be limited to the total amount of kVA capacity off of these. Let's take a look at what that actually looks like. Over here, we have got a delta secondary that's supplying a balanced three-phase load over here. And I've got transformers that are rated to 12.5 amps apiece. And what I can do is I know that my I line is equal to my I phase times root 3, which is what they've done over here. They've taken this phase value of 12.5, multiplied it by root 3, and they came out to this value down over here, 21.65. And if they have got 21.65 amps, and if this source over here, it's a delta source, is 240 volts over here, they are able to go and figure out the kVA at, well, basically they're going to be able to go and figure out the total kVA of this bank as being 12.5 times 240 times root 3. This is going to be my I line. This is going to be my E line. This is going to be my root 3. And when you multiply all of that together, you're going to go and find out that the overall kVA capacity of this bank as is going to go and be 9 kVA. Perfect. 9 kVA works for us. If we take the same transformers, and if we actually looked at what our individual transformers are for their individual amount of power or VA that they could each do, I could say that if this is 12.5 amps and 240 volts, I know that this can therefore, because we're only looking at a single at a time, we don't need the root 3, 12.5 times 240, which tells me that that is a 3 kVA transformer. This makes sense. 3 kVA transformer that we would go and have over here, another 3 over here, another 3 over here, that our output should be 9 kVA. Let's take a look at what this would look like inside of a open delta situation. In an open delta situation over here, we now have got some limitations. Remember that before we could look at combining two currents into a node over here. But now, all of a sudden, this whole section inside here is missing. There's no current to go and combine, which means that the only current that we could possibly get out is going to be 12.5 amps that we are going to go and get into this thing. So my I line has dropped fairly significantly. My new I line is now going to be 12.5. 12.5 I line. And if I multiply that by my E line, which is still going to go and stay the same, we're going to go and put that in as being 240 over here, my E line. And then if I multiply that by root 3, I'm going to go and get my total kVA that I'm going to be able to go and put out. So we're going to multiply those together, 240 times 12.5 times root 3, which is going to go and get me to a value of 5,200. 5,200 VA or 5.2 kVA, whichever one that you would prefer to go and use. If we then had to go and figure out how much current I could get through each individual load off of here, we're going to then go and take whatever we had for a total VA that we can supply out of this. We will take that total kVA and we can divide that down to a balanced three-phase load if we want. Or if I want, I can go and take my 12.5 that comes in, and I can go and say that I phase is equal to I line divided by root 3 for a delta. So I could do that as well, where I would just go and take the 12.5 divided by root 3, which would then kick me down to a current value that I would have off of here of 7.2 amps. That's one way to get it. The other one would be to go and take my total kVA capacity and divide by 3. Let's just go grab a calculator. We know how many total VA that we have, 5,200 VA. And if we take that 5200 VA and we divide it by the number of phases that we're putting it across in our load, that's going to tell us how many VA per phase. So I'm just going to take, 5200 divided by 3 tells me that each phase of my load, or each of those 3 individual load elements, is going to be taking 1,733. And if I take a look at this, I know that I had a 240 volt system that was supplying this, so therefore each of these is going to go and see 240 volt because my line voltage is the same as my phase voltage anytime that I'm looking at one of these. So I can go back to this one over here, my value of watts per phase of 1733, and divide this thing by 240, which gets me to a value of 7.2 amps. We'll just drop those numbers on there, 1733 watts per phase that we are going to go and have over here. You could add all of these up. If you would add all of these up, you'd also end up back at that 5200 watts. What we see overall is we see a great reduction in the total amount. Although we know that each of these individual phases over here should be able to go and put out 3 kVA total, we see that what we're actually getting out is 5,200. That's not 6,000. If I had 3,000 plus 3,000, that would get me 6,000. We see that the actual amount that's out of here is going to be less than that. And it's just due to the fact that they are operating in this open delta configuration. The percentage that they're going to go and have is, well, depending on how you want to look at it, 2 different ways that we can go and take a look at it. I could go and take 9 kVA, which is what it would have been as a good bank, 9 times 0.577. 0.577 is a special number. It is the inverse of root 3 to the -1. So I could go and say that this thing is going to be times root 3 to the -1. Take 9,000, multiply it by 0.577, and you will for sure end up at that same value over there of 5,200. The other way that you could go and look at this is you could say of the 2 windings that I have over here, the 2 windings should have 6,000 VA that they should be able to put out. But if I go and take that 6,000 and multiply it by 0.866, that's going to go and get me to 5,200 as well. So either one of these works perfectly fine for determining what the total kVA capacity is going to be of this, whether you want to go with the 86.6% of the 2, or if you want to go with the 57.7% of the entire bank, or if you just want to go through all the math and verify these. Line current in open delta secondary currents over here. The next couple of slides are going through a bunch of line currents that they're looking at. And they're going through a bunch of vectors over here, the current that's going through in the loads. This is not inside of the source. What the next ones are going through are all of currents that are happening inside of there. And so we're going to have 3 currents inside of there. We're going to have 1 current that's going through A to B, C to A, C to B, etc. And then they're just going through a bunch of the vector addition of these things to go and figure out what they are. I'm not actually going to go through it because it doesn't really prove a whole lot. It's impressive that somebody has placed this inside of here, but it's not necessary for you to understand how to go and do all of these. By all means, like I've said before, the videos, I'm not going through everything inside the book. I still expect you to go through everything inside of the book, but go ahead, look through that one yourself. I'm going to skip past it and get back into my open Y, open delta over here. Last connection that we have to go and look at over here is going to be what they refer to as an open Y, open delta. And this is what the open Y, open delta looks like. Primary is going to be connected as an open Y. And then the secondary is going to go and be connected as a open delta. And what they're doing is they're saying, this is my high voltage side. And here, we're just going to go make this one over here. And then they're going and taking these two and they're moving them over. Ooh, that's the wrong thing that I grabbed over there. They're moving them over like this. And they're creating a new transformer, an open delta, on this side right over here, utilizing those 2 vectors that they had before. This one that's down here on the bottom, although they show it as an actual line inside there, that's where the actual open itself is. And you'll notice well that once again we've got that 30-degree phase displacement between A to neutral, and then we're taking that A to neutral. We're rotating it up 30 degrees, so now my A to neutral point is going to be right over here. Couple of things that I do want to go and point out over here, right below the picture of that one. They say this connection is used in rural areas where most of the load is single phase. In areas like this, the supply authority may only run 2-phase conductors and a neutral, and then it allows the supply of small 3-phase loads. I've got a couple of cousins that work for BC Hydro as linemen. They work out here in the Fraser Valley, all throughout the Fraser Valley, as well as up north in the Peace region. And I ran that by them because sometimes you just got to double check on the stuff that's written inside of the books. Both of them replied that no, they've got a lot of unique old stuff on there, but they don't have these systems. Inside of linesman's school, there's a separate school for that, by the way, they do go over how to do this connection, but they only go over this connection for something for emergencies. That if you end up having what you used to have as being a complete Y to delta type of system, that you could still go and reconfigure, take that other dead phase out of there, and then use this thing to still deliver load out there. So they're not really a utilized connection. As far as the actual transformer connections go off of this one, straightforward. You're just going to go and build a Y type of system for the open Y, open delta. You're going to build the complete system, same as you would normally build a complete system over here, all the arrowheads going in the right direction, etc. And then all you need to do is you just need to go and erase one of those. We're going to erase this blue phase right over here. And once we've erased that blue phase, it shows us that we've got on our Y side, the H2s connect together onto a neutral. H2s connect together onto a neutral on the Y side. And then we see the H1 of A connects onto A. We see the H1 of A is going to connect onto A, and we're going to see the H1 of B is going to connect onto B. Same with the secondary sides. On my A line, I'm going to have my X1 of A. So over here on my A line, I'm going to go and have my X1 of A. There's the A line, there's the X1. And then on my B line, I'm going to have my X1 of B. On my B line, I'm going to go and have X1 of B. And then I see that I'm going to have to go and complete those lines by going and making my last connection. X2 of A goes to B, and X2 of B goes over to C. X2 of A goes over to B, X2 of B goes over to C, like that. And that's our complete transformer connection for that open Y, open delta. Once again, according to actual linesmen that work on the job out here in lower BC as well as in northern BC, this is not something that is in use that you should expect to see outside of an emergency type of situation.